Okay, good afternoon, everyone. Let's get started. So last time we started to talk about the how to do linear regression with multiple variables. So the idea is we have a target variable, y, that's a real number, and we have d features, each of them scalars, and we're trying to predict y with each of those features. So this is a direct extension of what we did in the last unit. There we had a single feature, now we expand that to d features. So everything else is similar. We come up with a linear model, which means we say that y is approximately equal to an offset beta 0 plus scaled version of each of those features. This is, of course, just an approximation because there's going to be error in our model. But then we define our prediction y hat as that function of those features. And we would like to design these prediction coefficients, beta 0 through beta d, so that our predictions y hat are close to the true values y. And we do that using a data set of pairs of examples of y and all these different features. We put those features together into this vector x. So we have a boldface x, that's going to be a column vector. And here when we say x, boldface x sub I, that's the ith example of this vector. And of course we have examples of yi as well. And there's a total of n of them. So we'd like to know how to adjust these prediction coefficients to minimize our prediction error. So the first thing we did to prepare ourselves to do this is to write the model more concisely, where we said, let's stack all of our predictions, yi hat, into a column vector. So that's what we have over here. We have like y1 hat all the way down to yn hat. So we're going to call that boldface y hat. We want to write those directly in terms of our vector beta of prediction coefficients. So we can stack all of our betas together in this vector boldface beta here. And then we need to find some sort of matrix such that y hat is a times beta. And to do that, we took our feature matrix from before, but then we augmented it by adding this first column of all ones. And you can see that this works out because when you do this matrix vector multiplication, you can think of that as the first column of A times the first coefficient in beta plus the second column of A times the second coefficient in beta, and so on until you're at the end. And so that first column of A is going to multiply this beta, and that's just going to put a constant beta value in all of the different predictions here. Is that clear? Why we need that column there? Okay, so then we have, we should also think about how we're going to use this eventually. This is just our training data. Eventually someone is going to give us a new piece of data, we can call that our test data, and we want to make a prediction from that. So at that point, we're going to have to do something very similar. We're going to stick that as a row vector together with 1. So this is a longer row vector, and we can multiply that by beta to get this scalar prediction. Okay, so that's sort of the setup, just describing some of the linear algebra to make things concise and easy to work with. And then we can move on to how exactly we do the computations to find out the optimal beta. Okay, so the least squares problem, jump ahead here. Okay, so the least squares problem is we want to find the parameters beta, and we're going to use them as follows. Just like on the previous slide, we're going to have y I hat is beta 0 plus beta 1 times xi1 plus all the others, and finally ending up with beta d times xi d. And so we want that these yi hats are close approximation to the yi's in our data set. So we're going to use the same approach as we did in the previous unit. We're going to define RSS as the sum over all our samples I of our squared differences between the truth and our predictions. We can think of these as prediction errors. Epsilon I is what we called them last time. Maybe, I think to be consistent with our previous definition, we just need to swap these. It's not a big deal either way. And then these epsilon i's, you can visualize them as these little red lines that stick up above or below this regression plane. So this is just a visualization that we can do in the case of d equals 2, meaning we just have two features, and we can label them as x1, x2. And so in that case, instead of like a line, which is what we had in the last unit, now we have a plane. So this plane is going to be parameterized by three numbers: beta 0, which is the intercept, right? That tells us where it crosses this axis. And then we have two different slopes. We have the slope in this direction, and we have the slope in that direction. So with those three parameters, we can move this plane anywhere. Okay, this is the special case where we have two features. If we have three features, it's not so easy to visualize. There's this three-dimensional plane. You call that a hyperplane. It turns out that all the geometry, all the geometric intuition is the same, whether you're in more than 2 dimensions or 2 dimensions. So it's enough, you can get everything just by visualizing this. That tells you how everything's going to work for any D. Okay? So our objective, just like before, is to minimize the sum squared values of all those things that stick up. So of course, these are our yi samples. Those are the dots. The plane is our y hat as a function of x1 and x2. And we want to adjust those coefficients, adjust the location of the plane to minimize the sum squared deviation. Any questions so far? Is this making sense? Okay. I have like a third nods and a third blank stares. Are there any questions that could help to clarify some of the blank stares? No? Okay. Don't be shy. Question? Yep.
Should it be yi minus yi hat? Or is it different?
It doesn't matter because of the square.
Oh, that's true.
Yeah. So I changed it just because I wanted to define the epsilon in the same way that I think we did in the previous unit. I think it was defined yi hat minus yi. You don't actually need to define epsilon, but I'm just wanting to relate it to the picture on the right. Okay, good. No other questions? All right, so now we are going to get to some of the linear algebra mechanics to do this optimization. So here's what we have from the previous page. We have this definition of RSS. And if you remember your linear algebra background where you learned about norms, a norm is a way of measuring the length of a vector. There's different ways to measure the length of vectors. Like if I want to measure as the crow flies just from one spot to another, that's the Euclidean norm. That's what I'm showing here. But if I'm a taxi cab driver in Manhattan and I can't go as the crow flies, I have to go down one street and down another street, I would measure distance a little differently. Turns out that there's another norm you can use for that, the L1 norm. We'll talk about that more in Unit 4. But I just want to point out there's different definitions of the norm. We're going to be working with the standard norm or the Euclidean norm for now. Okay? And so that norm is just the square root of the sum of the squares of the elements of a vector. So that's the norm. Sometimes you'll see this with like a square on this side and without the square root. obviously that's the same. But the point is that this quantity is just measuring the length of the vector, or if you think about the vector parameterized by the numbers that make up that quantity, it's basically the distance between those numbers and the origin. Okay, so the reason why we're doing this is because norms, there's a lot of a lot developed in linear algebra about norms, and once you see a norm, you sort of know what it means, how to work with it. And the point here is that when you look at this definition of RSS and you look at this definition of the norm, you can see that RSS is just nothing more than the norm, squared norm, of the vector of the true labels y and the predicted labels y hat. Right, so does everybody see this? Just based on the above two definitions. So this is just a really concise way of writing RSS where you don't have to use a sum. Okay, we can write the RSS directly in terms of the vector of true labels and the vector of predicted labels. We can go one step further then, and we can write it in terms of the quantity we actually want to optimize, which is beta. So I'm just going to replace the y hat with a times beta. And now we have an expression for RSS, which is directly related to that beta vector. Okay, so this is sort of the standard way you'll find people referring to RSS as using this equation. And so it's good to know if for no other reason than that. Okay, so next we'll start working with this and we'll figure out how to minimize that. But for now, are there any questions about how we created that expression? Okay. All right, so we can just step back for a moment and reflect on what we've done. We're just applying this general machine learning recipe again. In this case, it's a slight variation of what we did in the last unit. So now we have a linear model that involves D features that relates those features to our target or our prediction, and it does so linearly. So the target is a shift plus a linear scaling of all our features, like this. That's why we call it a linear model. From another perspective, you can say that y has a linear dependence on the betas. So y is linear in betas as well as linear in x. It's linear both ways. Okay, in any case, we want to fit those betas. We're going to do this with data. We have to say how we want the fit to be done, like what exactly do we want to minimize. That's our loss, which in this case is RSS, same as last unit. And so the parameters that minimize the loss are just the vector of betas that minimizes the RSS. Okay. All right, so now let's figure out how we're going to do this. So it's, again, in spirit, very similar to last time. So we have this RSS, which we know we can write as this norm. So one of the first things to remember about a squared Euclidean norm is that, I'll just write it in a simpler way above. If I have, let's say, a vector C, and you take the squared norm of C, you can rewrite that as C transpose C. So we can always do that. That exposes, what the norm is doing. It makes it easier to work with. So we're going to do that here. We write this squared norm in terms of the thing inside the norm transpose that thing again. And now you can see we have a quadratic. We can expand this into the first times the first. And then we have the last times the last. And here again, let me remind you another linear algebra fact that's super important. If you have A, B, that quantity, and you want to transpose it, what you do is you reverse the order and transpose the contents. So you have beta transpose times A transpose. Okay, so that's what we did. That's why we have this over here. And then we have the cross terms. We have y transpose AB, and then we have the quantity AB transpose y. But it turns out that when you look at those quantities, let's say we have y transpose AB, And then let's also think about B transpose A transpose Y. Are those similar or different? Are they the same or different? So the first thing to realize is they're scalars, right? It's just a scalar quantity. What happens if you transpose a scalar? Nothing. So the only thing that's different between this and this is I wrote one as a transpose of the other, right? I flip the order and I transpose all the elements. So because these are transposes of each other and they're scalars, they're identical. So I'll put an equals there. And that's why there's only a single cross product term with a 2 in front of it, is because I combine those two. Okay. So anyway, this is how we can express RSS in terms of, you could say, a polynomial of this vector beta. And you can see that there's one term with no betas, there's another term that has a single beta, and then there's a third term which has both betas. So basically this is a quadratic. Turns out it's a quadratic in this vector, so in terms of multiple betas, but still it's quadratic, and if you plotted it in the case of two coefficients in the beta vector, you would get this picture, which you can see is this paraboloid. It's a parabola in both directions. And this is exactly the same picture we had last time. So again, the intuition is all the same as last time. The only detail is now we have a whole bunch of coefficients in beta. We can't really plot more than 2 at a time, but the intuition is the same regardless. Okay, so our technique that we're going to use over and over again this semester is say, this is our cost. We want to minimize it with respect to these parameters. Let's just find the location of the parameters where the slope of the cost is 0. The slope, when you think about something that has multiple dimensions, the slope is called the gradient. So this is how you express the gradient. It's a vector. You take the partial derivative of RSS with respect to beta 0, beta 1, and so on, all the way to the last one is with respect to beta d. So it's just a vector of all the partial derivatives. We want to set that whole vector to 0 because that means we're at the very bottom of our cost. Very bottom is where the slope is 0 in every direction. Okay, so this is the same as what we did last time. And we also said last time that there's this other issue which we should just be aware of, that we want to make sure that the bowl is pointing up in all directions. And we said that you can do that using something called a Hessian matrix. So here I'm being a little bit more explicit. The Hessian matrix is a matrix of all the second partial derivatives. So you have like d squared over d beta j beta k for all the different j and k's. So that gives you a whole matrix. You have, let's say, maybe j going down one dimension, k going down the other. That gives us a whole matrix. It turns out that if you compute that for this RSS, imagine taking the second derivative of this with respect to beta, it goes to 0. If you did it with respect to this, the first derivative would give you something, but then there's no more beta, so when you take the second derivative, that goes to 0. And the last thing is you would take the second derivative, you compute this Hessian for this, and it turns out you're going to get 2 times A transpose A. We don't have to worry about those details right now, but we can see exactly what it is. And what we need is that matrix is so-called positive, semi-definite, and it turns out, and symmetric, it turns out because of this particular structure that it always is. So we're going to get back to that in a few units, but there's a few things that are sort of behind this idea of just setting the gradient to 0. Just wanted to be clear about them, but not to belabor them at this point. So that's our point, is find the place where the gradient is 0. Here's the plot where you see all the gradient arrows, and you can see that right at the center, the arrows have length 0. That's where the gradient is 0. Okay, same ideas as last time, just a little fewer more details this time. Is everybody good so far? Or any questions? Okay, so let's figure out how we can set this gradient to 0. So this is what we have for our RSS. Seen this a few times. This y hat I, we can write it like this. So what I'm doing to write it like this is, remember that we have this equation y hat, the vector, is A, the matrix, times beta, the vector. So let's think about what happens if you look at the ith entry in that vector. Try to visualize this. You have a matrix A, you have a vector beta. We're looking at the ith element, so that means we're pulling out this row of A, and that's going to multiply times this whole column vector to get the ith element y hat I. Is that clear? Right? So if I want to write that y hat I can write it as a vector inner product where I take the first guy here times the first guy here plus the second times the second plus the third times the third and so on. That's what this is showing. So I'm taking this matrix A here. Actually, I'll put it in red because the whole matrix is A. And this is my notation. I think you saw this in the homework. This is saying I'm extracting the ith row and jth column from that matrix. And I'm going to give that a name. This is really a definition here. I'm calling that thing little a ij. And so now that I have names for these quantities in here, these are the aij's. They all have the same I. J changes as we go across and as we go down. J is our index. Then we can write that y hat I as a sum over all the different j's, starting at 0, going up to d, of this aij times beta j, right? This times this plus this times this and so on. Okay, so I'm being really slow with the linear algebra just because I want to make sure that everybody's with me. I'm going to assume you guys are going to get good at this and we're not going to belabor all these details too much longer, but I just want to make sure everyone's on the same page right now. Any questions so far with what we have here in the first line? Everybody good? Okay. So this is the thing we need to set. We need to basically set this whole thing here to 0. This is our goal. Want to find the betas that do that. So you can see if this whole thing is the 0 vector, that means that individually each one of these guys is the 0 scalar. So I just want to set each of these guys to 0. So let's first of all derive an expression for the partial derivative of RSS with respect to the jth beta coefficient. Okay, so we have to do this again using the chain rule. So when you think about taking, let's say, d beta j of this, the first thing is you move that through the sum because differentiation is linear. So you move your d beta j here, and then because of the square, you use the chain rule. So you do 2 times this times the partial derivative of this inner thing with respect to beta j. Right? And then, so this is obviously not a function of beta j, but the second one is. So what is the partial derivative of y hat with respect to beta j? Let's look at this expression. And maybe I'll be just a little bit more explicit. Let me call this j prime, because we don't want to have multiple things with the same name. So I'm using j prime as the j that's in the sum, and I'm using j to index which one I'm taking the partial derivative of. So imagine now that I'm taking the partial derivative of this with respect to j. So there's a whole bunch of terms in that sum. Only one of them matches j, right? All the ones that don't match j, the partial derivative is 0. So there's only one that remains. And that's going to be that one is going to have aij bj, where now j is the one that matches this j. So if I take the partial derivative of that with respect to beta j, what do I get? aij. Okay, so basically this is the result of what we did. So we have the 2, that came down over here. We have this middle thing here. When we took the partial derivative, there's going to be a minus that showed up here. And then finally, the partial derivative of y hat I with respect to beta j is just that aij, which ended up here. Okay, so that's where we got this. Any questions on that part? Yeah.
So how does it just come out to aij, beta j, if it's j prime now?
So there's a j here. That has a specific meaning. We're looking at the derivative with respect to the j. Whenever you write a sum like this, that variable is like a temporary variable that only lives within the sum. And you could change it to whatever you want. Generally speaking, you don't want that variable to match some other variable which already has a meaning, because it can be confusing. So I just changed it to j prime so that it didn't clash with this one. So I just changed all these j's to j prime. And now I said, you know, what is, this is what I did. I said, what is d beta j of the sum over j prime of ai j prime beta j prime? And the first thing we realized is only one of the terms in this whole sum even depends on this. So that's the only term that can survive this differentiation. Right? All the other terms drop away.
Prime happens to equal j.
Yes, exactly. And that term that survives is this. And then when we take the partial derivative, we finally get aij. Okay, so that's where this guy came from. Yeah.
So the differentiation we read here, is the differentiation even if you just take it inside the summation, right?
Yeah, the summation's over I, so that's, there's no problem just bringing it in.
And then you remove the square and say that because you can just put it as double.
Yeah, so I was using the chain rule.
Yeah, my question here is that that it only applies if it is a very small quantity, right?
No, this is just basic calculus, just differentiation with the chain rule. It works for in any case. Yeah, it doesn't need to be big or small. Okay, so any other questions? Okay, so we got this expression. So what we really want to do is we want to express this back in terms of vectors and matrices. So we have to pack it back in terms of vectors and matrices. And this is why I included some of the problems on homework 0, where you're given a sum and you have to write it in terms of the vectors and matrices that define the variables in that sum. So here, I think it's a little bit easier to go backwards in terms of explaining it. So let's say we have this matrix A, which I have above, and we are indexing the rows by I and the columns by J. So when I transpose that A, I'm actually switching it. I'm now indexing the columns by I and the rows by J, which is good because these Y's, if you remember, they are indexed by I, and this needs to match, right? We need to have the right dimension here has to match this dimension. So these I's have to match those I's. So if I want to write this A transpose Y in terms of, you know, what's actually going on in that sum, I would be doing a sum where I'd look at, let's say I freeze a particular value of J. So now I'm doing something like this, but with A transpose. So I have this is A transpose. This is Y. I'm going to look at the jth row, which is going to extract those elements. And I want to do this multiplication, where I multiply these times these. So now I have this variable, this temporary variable I, which goes across the columns, comes down this way, and I can write that using this sum here on the left. So I have the first one times the first one plus the second times the second, and so on. And I'm just using I to index what's first and what's second, and so on. So this is where I get Aij being those elements, and Yi here, or Yi hat, being those elements. So this is how we move between the sum representation and the vector matrix representation. So this is something that probably just takes you a bit of practice to get used to, but it's sort of important to be able to do this for these derivations, is to usually it's much easier to derive things with scalar derivatives. There is vector calculus, it just gets a bit complicated. You can take derivatives with respect to vectors and matrices, but unless you know what you're doing, it's a mess. So for this class, we always come back to scalar derivatives to make this very clear, and then we rewrite them in terms of vectors and matrices. So that's what we're doing in this step. Okay, so basically, this thing is like the jth element of this vector. So this is the jth element of the gradient equals the jth equals this. We can go one step further and we can just plug in the expression for y hat, which is a times beta, to rewrite it like this. And now, the reason I'm doing this is I essentially want to know, how to describe this as a vector. So this is just the jth element of my gradient. This is the jth element of this vector. Therefore, my gradient must be this vector. Actually, -2 times this vector. So does that make sense? We want this guy to be 0 for all the elements, and that is going to be true if this vector is 0 for all of its elements. So that's where this comes from. We want this to be the 0 vector. Okay, so, and we're almost done now. Essentially, we need to find the beta. This is like beta least squares. We need to find the beta least squares, which satisfies this equation. This is pretty straightforward. The first thing we do is we just multiply this out. We have A transpose Y, gives us this. And then we have A transpose times A beta least squares. Because of the minus sign, we can move that to the other side. So this equation is equivalent to this equation. And then what's the last step if I want to extract beta least squares from this? What did you learn in your linear algebra courses? Assume that this matrix is invertible. What do? Yeah, you take the inverse of that matrix, you multiply on the left, both sides. So if I take A transpose A inverse and I multiply it on the left here, it gets rid of this, it just cancels it. But then I have to multiply it on the right as well. So I can finally get beta least squares equals A transpose A inverse A transpose Y. Okay, and here we're assuming that this matrix is invertible. We'll talk later about what happens when it's not invertible, but it usually is invertible. One of the cases where it's not invertible is when your model is more complex than the number of samples in your data set. In that case, you have a problem. You can't necessarily solve this. You can approximate it, but you can't solve it. Usually in machine learning, you have way more data than you have parameters to fit. So it's not going to be an issue. So that's our assumption for now. And like I said, we'll talk about this in more detail later. Okay, so essentially what we did is we started with this RSS. We wrote it in terms of our beta coefficients. We set the partial derivatives of the individual beta coefficients to 0. Then we figured out how to write that in terms of matrices and vectors. We found that this whole vector needs to be equal to 0, which gave us this equation. And then we just worked it around a little bit, solved this system of equations, and we finally get our least squares solution for beta. Okay, so this is how we can solve this, this fitting problem. Create these matrices, vectors, and then just plug this into your favorite solver. All right. So, all right, any questions on this? Yes? Yeah, that's right. D is always equal to the number of features for us, as you can see. So we're always going to use D for that quantity throughout the whole semester. And then we'll always use N for the number of data samples. Yes?
So if we're assuming that A is invertible, won't that equation just simplify down to A inverse times Y?
So again, A is not even square usually, so A is not invertible. But what's invertible is the A transpose A. That's a square matrix, always. And it's going to be invertible if you have enough data and if the data is random enough to give you that inverse. Okay, great. Any other questions? Okay, so another thing that we can do is we can ask whether we had a good fit or not. Actually, this slide is identical to the one in the previous unit. So we have RSS, but the problem with RSS is that it gets bigger if you have more samples. It gets bigger as the variance of targets Y increase. So what we would like to do is we'd like to normalize it by dividing by the number of samples, dividing by the variance of Y, and then you get a normalized quantity that's interpretable. And you could use that, but most people use 1 minus that. So 1 minus RSS divided by N divided by sigma Y squared. Or sorry, we call it SY squared. And that thing is called R squared. So you use the same idea as we used in the previous unit, and everything else applies. You know that if you have the least squares prediction, R squared is always between 0 and 1, can never be above 1, it can never be negative. But if you have a non-least squares prediction and it's a bad one, it could be negative. So, yeah, but everything else is the same as last unit. All right. Any questions on this? Okay. Yes.
So you could really mess up the model if you have a bad diversity of data?
So no matter how bad the data is, if you use the least squares model, you will never get a negative R squared. So we said.
You said the invertible, it has to have enough randomness for it to be invertible.
Oh, the matrix.
Yeah.
Yeah. So I don't know if you know about low rank matrices, but you can have a square matrix that's not invertible because certain eigenvalues are 0, and that can occur. For example, if you have if all your x's are exactly the same number, and you looked at what that matrix ends up being, it would have a rank of 1 or 2, meaning you would have a lot of 0 eigenvalues that wouldn't be invertible. So so that's just kind of, yeah. Don't want to get too much into that, but generally if you created a random matrix with random 0 mean Gaussian values, and then you computed this A transpose A and looked at the rank, looked at the invertibility, it would almost always be invertible as long as it was the right size. Okay. So, all right, so this is R squared, same as before. So now there's kind of an issue with this expression. It's correct, it works, but when you look at it, it's just really not very interpretable. It's really hard to understand what is going on, because this matrix A, it does not include only your features, but it includes these extra ones. And so, for example, you might ask the question, well, last unit, we also derived a beta that would hold if I have one coefficient, but it's not at all clear how that expression is the same as this expression, even if we only had one coefficient, one feature. So can we do something? Can we rewrite this in a way that is more interpretable? And the answer is yes. And we'll learn a few things along the way. So, okay, so in terms of interpretability, we're kind of back to this picture here. The first stage is to separate out that first coefficient, beta 0, from all the others. And this is in part because it just works in a different way. All these coefficients, beta 1 through beta d, they multiply a feature. But the first one doesn't multiply any feature. It's kind of special. So this intercept coefficient, we're just going to pull out and treat separately. So we're going to put it here. And then we're going to define a new vector, which we're going to write as beta sub 1 through d. And that just has all the remaining coefficients in it. So our total beta, this is in transposed form, has that first coefficient and then all the other coefficients. In other words, the intercept and all the slope coefficients split into two parts. Okay, so is that pretty clear? Okay, so then if we write things that way, you can see, to make a prediction y hat, you would take the offset, the intercept, plus an inner product between this beta 1 through d and your x. An inner product is another way of saying this vector transpose another vector. Sometimes called a dot product, inner product. Okay, so we're going to use this new notation in some of our development that's coming up. All right. But before we do that, let's talk about some statistical quantities. And these are essentially the same statistical quantities we talked about last unit, except now some of them are changed because we might have a vector instead of a scalar quantity. So for example, let's think about the feature means. So we have feature vectors now, not scalar features. We have vector valued features xi. So each one of these guys is a vector. If I average my xi's over my entire data set, I get another vector, which we're going to call x bar. That will be the sample mean vector for your features. If you look inside that x bar vector, you will have these elements like the first one, second, and so on. And it turns out, it's not hard to see, that the first element in your x bar vector is actually the sample mean of the first element in all your feature vectors. So this x bar 1 is the average of xi1 for all the other i's, for all the i's in your training data. Does that make sense? And so these are like just the sample means of the scalar features in your data set. For the targets are still scalars, so y bar is the same as last unit. Okay, now this is the means. What about the variance? So let's think back to the last unit. This is our definition for the variance of x. So you would take xi, you'd subtract its mean, and then you take xi again, subtract its mean, and you multiply them together. I think last time we wrote this as a square, but you'll see why I'm writing it as this times itself now. And then you average that. So now what happens if xi is a column vector? We can still do this. We just need to transpose. I'll even put the transpose here because it doesn't change if it's a scalar. I'll just transpose it. And now I get this definition. This thing is called the sample autocovariance matrix. Okay, so why is this a matrix? Well, the first quantity is a column vector. The second quantity is a row vector. And if you multiply a column vector times a row vector, you get a whole matrix. So this guy, the sample autocovariance matrix, is a direct generalization of the variance to multiple dimensions. We'll have a lot to say about this matrix when we talk about PCA later in the class. It turns out that if you look at the diagonal elements of this matrix, those are the variances of each of the different features, sample variances of the features. Okay. Then we have our cross covariance vector, which is a direct generalization of our covariance from last unit to where these x quantities are vectors. So in this case, the first one is a vector, the second one is a scalar, so when you multiply those, you just get a vector. Okay, so this is why we're writing this with a little s, it's just a vector, but this one is a whole matrix. Okay, so conceptually, these are very close to what we did before, it's just that now they work with vector valued features, vector valued features, features greater than 1. Okay, everybody good with this? All right, so now, very similar to what we did last time, we're going to come up with alternate expressions for these quantities. So we start with the definition of the sample covariance matrix, and we rewrite it by expanding this quadratic. So we have the first times the second here, the first times the first. We have the last times the last. That's going to give us this. And then we have the cross terms. So we're going to have xi times x bar transpose and x bar times xi transpose. So here's the x bar times xi transpose. Notice that because the x bar doesn't depend on I, we can move it out of the sum because of linearity. And then we can the average, we can apply the average just to this xi bar, And then what is this? If we do that, what is this whole quantity here in the brace? It's just the x bar transpose, right? It's just the average of x. That's a vector. Actually, since it's a vector, I'm going to put a little underline under it. And then we have the same thing over here. This is, again, is our x bar vector. So finally, you can see that this is minus x bar transpose, another minus x bar transpose, and a plus x bar transpose. So finally, we get the first term, which is the sum over all of our xi's. And then we have minus x bar transpose. The reason why this formula is convenient is because often this quantity will come up in a derivation, and now you know that you can write that quantity as the sample covariance plus the outer product. This is called an outer product of the sample means. So that's the outer product, and then the inner product would have the form x, just notationally. Inner product gives you a scalar, outer product gives you a matrix. Very different in that sense. Okay, is everybody okay with this expression? Yeah.
How did we get rid of the middle terms?
Oh, so this, all the last three terms are, this is just negative of this one. You see how this is like x bar times, okay, so this whole thing is x bar transpose. So this is minus x bar, that's like just minus this. So basically, you could say this cancels this, and it leaves this.
Yeah.
Right? Okay. Okay, so then the other expression is, we do the derivation very similarly. We start with the definition from the previous page, and then we expand out this quadratic, and we have xi times yi here, and then we have x bar times yi here, where we move the averaging, or we move x bar outside the sum because of linearity. It doesn't depend on I. For the next term, we have our xi times y bar, like this, and then finally we have our x bar, y bar here. So, and now you can see that this first brace, this is nothing more than the scalar y bar. And then down here, we have nothing more than the x bar vector. And similar to before, this quantity cancels this one, and it leaves the first and the third. So we're going to have 1 over n times the sum over I of x I times yi minus x bar times y bar. Okay, and that is convenient because sometimes this shows up, and now you know that that's nothing more than the cross covariance minus the product of the means. Okay, so we're almost ready to use these quantities. Is everybody good? All right, so let's finally do this derivation for the an alternate expression for the minimum, the betas that minimize the RSS. So actually, I'm noticing that there is looks like there's some small typos here. So this should be the beta 1 through d vector, and this should also be the beta 1 through d vector. Okay, so what we're going to do is we are going to take our partial derivative of RSS first with respect to beta 0, beta naught. So here is, if you remember, this is how we are rewriting this whole thing as our minus yi hat. So we're splitting that into minus the intercept minus the effect of the slope coefficients. And now we want to take the partial derivative with respect to beta naught. So we use the chain rule. We move this through the sum. That gives us sum I equals 1 to n. Then we take the partial derivative of this with respect to beta naught. So we bring down the 2, put that over here. And then we have the whole thing. I'll just write it simply as yi minus y hat I for now. And then finally, we have the partial derivative of this inside term with respect to beta naught, which is just minus 1, right? So this is going to give us a minus in front of there. Now we can also look at the partial derivative with respect to any of the other j's, where j is 1 through d, somewhere in there. So now, what's a little tricky is that beta j is actually buried in this inner product. So to make sense of that, let's expand that into a sum. Let's come up again with this j prime as our temporary summing variable. I'm choosing that to be different than this j. So this is just a row vector times a column vector. And to do that, you just take the first times the first plus the second times the second and so on. And that's where we get this xij times beta j summed over all the j's from 1 through d. Now that we've written this explicitly in terms of this scalar, it's easier to do this partial derivative. Okay, so to do the partial derivative, we're evaluating this. We can move this through the sum. So we're going to have sum of I going from 1 to n. Then we're going to have yi minus beta 0 minus xi transpose beta 1 through d. Okay, so that's chain rule. I bring the 2 down, put the 2 over here, and then I have what's the inside of this here, and then I finally have to do the partial derivative of the inside with respect to beta j. So none of this stuff matters for that, but as you can see, I'm going to have a minus, so I'll put the minus out here, and now I'm going to have the partial derivative of this with respect to beta j. So there's only one of the terms in the sum that matters. It's when the j prime matches the j. So in that case, I'm going to have xij times beta j. I take the partial derivative of that, and I just get xij. So I'll put that here, xij. Okay, so we're almost done. So to make both of these convenient, let's multiply. So we want to solve this. 0 equals this, 0 equals this. Let's multiply both by minus 1 over 2n. That will change the minus 2 into a 1 over n. So in the first case, we get this expression. So here I've expanded out. This is the y hat I, expanded back out. And so now let's just distribute that sum. So we have this term, that's our y bar. We have the average of the beta zeros, which is just nothing more than beta 0. And finally, we have the average of this last term, which looks like this, but you can see that you can do the sum independently of the beta, and that's just going to give you your x bar transpose. Okay, so finally, what you find is that you get beta 0 is y bar minus x bar transpose times a beta vector 1 through d. Okay, so this is the expression for the optimal beta naught. And now when you look at it, it actually looks similar to what we derived in the last unit. Okay, So let me just try to just one more page essentially of derivation, and we can finish out this and then end the class. Everybody good? Yeah.
So what is meant by the second one, xij, the scalar x?
Xij. So that is the ith training sample jth feature. Yeah. If you remember, the very beginning we had like a whole matrix back over here. So these are all our xij's. They end up being those quantities. Yeah, so we have like, as you go down this way, you have I, which is the training sample, and as you go this way, you have J, which is the feature. And so I'll also be consistent all semester with using I for the training samples and J's for the features, just to try to keep things similar. Okay, so, all right, so we just have one more to do. It's very similar to the last page. So we want to, okay, so what we can do now is we can plug in this beta 0 in here, and then we can try to solve the rest of it. So this is what gives us, oh, sorry, this one is what gives us this. Yeah, sorry, this, I meant to draw that arrow. We're going to plug this into here. Okay. So this is what we have from above, and then we plug in our beta 0, and now we get, oh, let's see, maybe not, okay, not plugging it in quite yet. Let's distribute it first. So we distribute the sum, we get these terms. So this is just, if I look at this without anything else, this is just going to be xj bar. And finally, we have this times this, like this. Okay, now finally, we plug in beta 0 into here. And that gives us, we have no more beta 0, and now we have this stuff in there. So that's going to expand this into this and this. And what's nice is that that combines with the other sums to simplify. Okay, so first of all, let's write this in terms of a vector. This is the jth element of a vector, where this becomes a vector xi, this becomes a vector x, this one becomes a vector x bar, and this one becomes a vector x. So if you think about it, if you take that vector expression and you look at the jth entry, you get exactly that earlier expression. And hopefully now you can see that this is, we can use those alternative expressions. So we have S vector xy, that is where we get this. And then over here, we get minus SXX, the matrix, times beta 1 through D. Okay, so we're almost done. So you can see we want 0 to be every row in that vector. So that means that the entire vector is 0. That's what we have over here. And now we just have a linear algebra problem. We can write this equivalently as SXY equals SXX beta 1 through D. And if this is invertible, we finally get beta 1 through D is SXX inverse times SXY. So this is if SXX is invertible. Okay, so this is the rest of our expression for our least squares coefficients. And this is much more interpretable because it's based on statistics of the data. We have the autocovariance inverse times the cross covariance. And if you do a direct comparison, so this is what we just derived for our least squares beta. If you just think back to the previous unit, you say, well, what do these quantities turn into in the scalar case where d equals 1? This vector just turns into the scalar. The vector x bar turns into the scalar. This autocovariance turns into the variance. Cross covariance turns into this covariance. And in that case, you make these substitutions in there, and what you find is you get y bar minus x bar sxx sxy, and you get sxy divided by sxx. And these are exactly the expressions we derived in the last unit. So now we can see a direct correspondence with that derivation in this one. Okay, sorry for going a little bit over. The next thing to talk about is how we implement all this in Python. So no more math for most of this unit. Well, a little bit, but not too much more. More about implementation next time. All right, see you guys on Friday.